So as far as the message authentication code is concerned, this method applies very similar to the message digest, but seems to be similar to the message digest, but there is a simple difference, because message authentication code is again going to frame a message digest or the signature or a certain fingerprint related to the message. But the difference between the message digest algorithm and the MAC is, since message digest algorithm does not use any cryptographic process, but there are certain cryptographic process which is involved in the calculation of message authentication code. And of course, since there is a cryptographic process which has to be adopted, it will be using the sender and the receiver will be using the shared secret key. It means it works on the symmetric cryptography. So this is the way by which the MAC is being calculated. What we used to do, we take the message and we apply the shared secret key on the message to get its hash value. But before that, the sender and the receiver must have to agree on the shared secret key. If there are two people in conversation, A and B both should know about the shared symmetric key, that is K. So what this sender used to do, it takes the message, applies the key on the message to get its hash value, and that hash value is known as MAC value. And then along with this message, this hash value H1 is sent to the receiving end. So when B is going to receive this message, it again calculates its MAC value by using the shared secret key K. It tries to find out the MAC value, and that is the H2. And if it also has received H1, and if this H1 and H2 are same, the receiver will be able to know that first thing, that H1 is equal to H2. It means there is no alteration in the message. The second significant point with this is, since the users are using shared symmetric key, so the receiver will be able to judge, authenticate that this message indeed has come from the sender, because the shared secret key is being shared between A and B. And since A is calculating its MAC value with the help of shared secret key, B is calculating its MAC value with the shared symmetric key. So if it is able to find H2 is equal to H1, receiver B will be able to show that this message has come from A. Meaning thereby any other people, any other attacker in between, if it tries to find M and it uses a key to calculate the MAC value and send it to the receiver, but this receiver and the attacker does not share the symmetric key. So whenever receiver is going to receive that kind of message, it will be calculating MAC, and MAC will not be able to match because of the property of the message digest. Because until unless the message is not the same, it is not able to calculate, and the digest value is not going to same because the keys are different. So this is the way how MAC is being calculated. Then what is the significance of this message authentication code? The first significance of the message authentication code is the MAC assures that the receiver, MAC assures the receiver that the message is not altered. Second, the receiver is assured that the message indeed came from the correct sender. So these two are the two important points which is going to give the significance of message authentication code. Now, but there is a difference while we are using the symmetric key cryptography. Whenever sender is sending any message in the form of an encrypted message, the receiver is going to decrypt it. But in case of MAC, nothing is being done. Both the sides, we are doing the same operation that is called the encryption. In case of sender, it is encrypting the message M with the help of K to get H1. And whenever receiver is receiving M, it will be encrypting with the help of K to get the value of H2. So there is no decryption process. It means the cryptographic algorithm which is used, the shared symmetric key which is being used, or symmetric key cryptography which is used, is not reversible. It is a single way. And that is why sender and the receiver both are using encryption process only, and no one is using the decryption process only. So this is how the MAC is being calculated, but later on, since we are encrypting the message itself with the help of shared symmetric key, so of course the message will be long, so the encryption process will be a time-taking process. So people come with the idea, why not to use the secure hash algorithm or the message digest algorithm to calculate the MAC. And that gives the idea of HMAC. And that HMAC is known as hash-based MAC. And this hash-based MAC or the HMAC, hash-based MAC or the HMAC is being used in the IP security, Internet Protocol security in the secure socket layer, whenever we are using the internet. So the idea of HMAC is just to reuse the existing message digest algorithm and how it is being done. So HMAC is known as hash-based MAC message authentication code. And how it works. So whatever is our original message, first of all, we apply the message digest algorithm such as MD5 or SHA1 to get the message digest of the original message. And then instead of encrypting the message, we encrypt the message digest of the message by the help of key so that we will be able to get the MAC. Now, this is the way by which HMAC works, but we have certain more things that how HMAC is going to work. And for that, we have some variables used in HMAC. The first one is the MD, that is the message digest or the hash function. M is the input message whose MAC value has to be calculated. L is the number of the blocks in the message M. B is the number of bits in each block, because whatever is the message, we convert that message in the blocks. And B is the number of bits available in each block. K is the shared symmetric key, which is used in HMAC. And IPAD is used, it is an 8-bit string repeated B by 8 times, means how many number of bits available in the block. It will be repeated that times, B divided by 8. And OPAD is also in a string, different string from IPAD, repeated also B by 8 times, where B is the number of the bits in each block. So how it works? The step number 1 of the hash-based MAC algorithm says that, first of all, it is necessary to make the length of the key and the length of the block of the message equal. Suppose the block size is 64-bit and the key size which we have taken is 32-bit. So anyhow, there is a discrepancy in the size, number of bits available in key and the bits in the block. So we have to make it equal. How we can make it equal? If both are same, then we do nothing. But if the length of the key is less than B, number of blocks, in the case block size is 64 and key size is 48, then in that case we append 0 bits to the left of the case so that the length will become equal. And when the length of the key is greater than the block size, then we hash the k to reduce the its size equal to b. We truncate the value of some of the bits of the k so that it will become equal to. So the first step of HMAC is to make the length equal to the number of the bits available in the block. Once we are able to do it, we do calculate the value of S1, and this value of S1 is calculated with the k, that is key, and the iPad, and these values are XORed, and it will become S1. Now, whatever is the size of k, suppose it is 32-bit, so iPad will be also of 32-bit. So these two are XORed to get the value of S1. And this S1 is appended with the original message, so that original message will become S1 plus the original. In abstracted form, it will look like this. Now, with the help of this appended original message with the S1, we take the message digest. We apply the message digest algorithm to get the hash value. So hash value is not calculated on the original message, but it is calculated along with S1. When S1 is appended with the original message, then only hash value is calculated. Once we are able to do it to calculate the value of S1 and it is being appended with the original message and we have calculated the value of H, the next step is to XOR the value of K with OPAD to get S2. And once this S2 is calculated, this S2 is appended with the hash value, so that in abstracted view, it looks like S2H. And this S2H, again, we apply the message digest algorithm to calculate the MAC. And this MAC is known as HMAC. This is the total process which is being done. First of all, the key is transformed to make it equal to the number of bits available in the block. And then we use iPad and XOR this iPad with the transformed key to get S1. Then S1 is appended with message M. A message digest algorithm is applied to calculate H. Then separately we take OPAD with transformed key and we XOR to get S2. And then H is being appended with S2. And then we apply message digest algorithm to get the HMAC. So this is the complete operation how HMAC is being applied. So this is the way how HMAC used to work. Of course, it seems to be very safe process. It seems to be very the process by which we are calculating the HMAC, and it is going to prove both the significance of the MAC, that is, the receiver is going to assure that indeed it has come from the correct sender, as well as the message is not being altered. So this HMAC value along with the original message is being sent to the receiving end, and the receiving end will also calculate the HMAC in a similar fashion and then try to match this HMAC to prove the integrity of the information which has been sent by the sender. But besides having the simple algorithm and calculating the MAC in the form of a HMAC, but this HMAC is having a little bit problem, that is the disadvantages. Of course, this MAC which is being produced by HMAC algorithm, it fulfills the requirement, but it is a little bit problematic. And the first problem which is associated with HMAC is the problem which is associated with the symmetric cryptography. As we know that the first and the foremost problem of the symmetric cryptography is the problem of key distribution. So if we are using for calculation of HMAC, we are using symmetric cryptography. So the sender and the receiver must have to make an agreement on a certain issue so that they are able to share the same symmetric key, secret symmetric key. And since there is a problem with the sharing of the symmetric key, so the problem also exists with the problem of key distribution in case of HMAC. Now, The second problem, which is related with the HMAC, is if the number of receivers are more. Suppose they one sender and there are 4 receiver. Then for every receiver, it has to have the shared symmetric key. Otherwise, if a sender is sharing the same secret key with the many people, then it will be difficult process. It will be difficult to identify that which one has sent. Because if there is a user A and there are B, C, D, E, 4 more receivers, and so what the sender has to do, if it has to maintain the integrity, what it has to do, it has to maintain the authentication also. So what it will do, either it will share the different symmetric key with the different user, or it will use the same key for all users. Suppose number of receivers are more, so if it is sharing the same key, suppose the problem is solved and authentication is not a problematic part, and number of receivers to whom the message is being sent is being used with the same shared symmetric key. Suppose this problem is also solved. Suppose the first problem is solved, second problem is solved, then the third problem, the authentication problem, that how to recognize that which sender has sent the message. Because if number of users are using the same shared symmetric key, so what will happen? Suppose there are A, B, C, D, E. There are 5 users and they are using same shared symmetric key. And suppose A is the sender and A has sent a message by encrypting, calculating the HMAC with the help of encryption process. So, and there is a receiver B, it has the shared symmetric key, it will open the message, try to make some changes, and we use the shared symmetric key to send it to the rest. So there will be an authentication process, because if 5 users are using the same shared symmetric key, then there will be a problem related with the authentication problem. Why? Because the receiver is not able to know that which sender has sent it, whether A has sent it, B has sent it, C has sent it, or E has sent it, because all the users are using the same shared symmetric key. Suppose this problem is also solved. First problem is solved, second is also solved, third is also solved. Then fourth one is the biggest problem, that is the fabrication problem. And for the fabrication problem, I can give you an example. Suppose there is a customer of the bank, and the customer is using the shared symmetric key. So whenever any transaction is required by a sender, it encrypts the message along with the MAC value to the bank, and bank does the transaction. But what will happen? Suppose the person who is working in the bank has some malicious intention. Since both customer and the bank are using shared symmetric key, so that person who is having malicious intention can use the shared symmetric key, can fabricate a message from which has can fabricate a message by posing himself as a sender A, tries to write a message and try to find out the HMAC, and receives it. And after the receiving, it makes the transaction, it debited the amount from the account of sender A into its account. That is why any kind of transaction, financial transaction, does not use the shared symmetric key. And that is the fourth problem. That is the fabrication problem. So all these problems which are associated with the HMAC, that gives birth to the digital signature algorithm. And digital signature techniques which will be used will be a little bit different from HMAC. And that is, we take the original message, we apply the message digest algorithm to calculate the message digest. Once this message digest has been calculated, we encrypt the message digest with the help of the sender's private key, which is known to sender only. And then it is going to create a digital signature. And then what sender will do, it will keep the original message along with the digital signature and send it on the open network, and it is being received by B. Now, how the B will be able to authenticate that whether this message which has been received is came from the sender A. So what it will do, it will receive the original message as well as the digital signature. Now it will apply, the receiver will apply a message digest algorithm to calculate the message digest of the original message which it has received. And it is also has received the digital signature. So first of all, it will apply the message digest algorithm from on the original message which it has received to calculate the message digest 2. And then it will apply the sender's public key to decrypt the digital signature to get the message digest 1, because it is the message digest 1 which is calculated by the sender, encrypted by its private key, send it on the network, which can be decrypted only by the sender's public key. So it will receive MD1. Now what it will do? Now this MD1 and MD2 is being compared because MD2 is calculated by the receiver. MD1 has been received in the encrypted form by the receiver. So if this MD1 and MD2 is equal, then it will trust and accept the original message. Otherwise, if it is not equal, it means it will reject the original message. So this is all about the